Hi everyone, here we are for the first lesson of week 2 in our remote or digital learning experience. The plan from here on out is that I'm going to post short videos just covering the content we would have in class, and keep in mind that this isn't meant to fill a 50-minute class period. This is meant to fill 2 days a week so that it turns into about an hour and a half to 2 hours of content. With these, I'd ask that you just watch the video through. You can take notes along the way. You can just sit back and watch. You can put it in half speed, you can put it in double speed. You can change how you present this, but I'd ask that you do take the time just to watch through this because I've taken the time to put it together. So what we're going to cover here is short mini lessons, like I said. This week I believe there's 2 or 3 of these. That's a little heavy just because we're jumping around on content. So where we left off, if you recall, we left off doing a normal distribution, that bell curve, and looking at different percents of the curve we found. Then we went on to a line of best fit, and we had left with a R value. And what I decided to do ultimately is, because the R value requires a calculator and it requires a lot of computation, we're going to actually just move ahead into the next topic we had planned. Now also, you're probably noticing I'm here. Part of the remote learning allowed me to stay at home with my son and still teach part of my classes. So I'm staying in statistics and I'm staying in pre-calculus. So those 2 courses are going to have me until further notice, or if we start meeting face to face at some point this year. So here we go. Let's dive into probability. This week we're looking at probability for the first part. So this would be the Monday session. And then on Wednesday, we're actually diving into Venn diagrams and something called set theory, which we'll touch on today as well a little bit. But set theory and Venn diagrams allow us to tie probability into those in the next week, and that will be something that makes our lives actually pretty easy when we start looking at some more in-depth problems. So this probability is something you've seen before. There's not going to be anything groundbreaking in what we talk about today. So where we're beginning, today we're talking about probability as a result from an experimental or theoretical experiment. So a quick overview of these two. Theoretical is what we see in theory. So it's if I flip a coin 10 times, I'd expect in theory to see 5 heads and 5 tails, or 50% of the time, because the outcomes are equally as likely to happen. The experimental probability is the outcome if I actually flip a coin 10 times. If I do that, I wouldn't necessarily expect every single trial or every single group of 10 flips to be 5 heads and 5 tails. We could say the experimental is 3 of 10 are heads, then 7 of 10 would be tails. So theory is what you'd see in a textbook or as expected, the generic end. Experimental is the outcomes that actually occur as we go through this. Both of these use the same terminology, but we're actually just going to start a little bit with some of the terminology with experimental probability. So this is just based on, like I mentioned, what happens when we actually run an experiment. Now, a few key words as we begin this. Trials are how many times an experiment is repeated. So if I flip a coin 10 times, I'd say I have 10 trials in that experiment. The outcome is the result I observe from those trials, and finally the frequency is the number of outcomes it's observed. So a trial we run and record the outcome as a frequency. So these all kind of tie together from one to another. I realize there's no periods here, I'm just looking at that, but that's okay. The capitalization's a little spicy or dicey too. We'll be okay with that. So when we think about probability, what we had when we did the normal distribution was we had a percent, which tells us what percent of the data or what percent of the time. Probability, we don't really tie into that way as saying like 0.5 of the time. We just say the probability of this event occurring is blank. And that blank is always between 0 and 1. So 0 would be impossible. It would be like, if today is Sunday, what's the probability that tomorrow is Thursday? 0. Certain always happens. If today is Sunday, what's the probability that tomorrow's Monday? Well, it's a 1 as the probability. These two don't happen very often, actually. It's what's in between. And there's a standard when we start running tests that we rely on in the probability of something to really be convinced that it's likely to happen, or that it's something that's significant. We say statistically significant is where we're headed later on. But between 0 and 1 is what probability always is, whereas percent is always between 0 and 100. We can convert between those one another. So if I have a probability of like 0.4, well, we can convert this into 40% of the time. I'd expect that based on what we're observing. So when we run an event or a experiment, the outcomes that we can have where we're headed are actually called sample space. So the sample space is every outcome that can occur. So if I'm flipping a coin, we'd say the sample space is heads and tails as long as it's a two-sided coin, which I don't know what a non-two-sided coin would look like. So one word where we're headed is set. A set is a group of anything. It doesn't have to be numbers. It doesn't have to be letters. It can be a set of anything. So like the alphabet, we'd say is a set of letters. We'd say even is a set of numbers. We can say odds are a set of numbers. Negative are a set of numbers. We can say we could even say Flathead High School is a set of students. I don't know along the way, but it's notated with the hardest symbol in math. If we were face to face, we'd have a competition for who can draw this. This is, oh my, I don't know, year 10 of me drawing this symbol and I still can't do it. It's the squiggly curly brackets. This just indicates a group of something. So set is with these brackets. I call them the curly brackets. I'm sure a lot of people have some other ways of doing it, but like you can make them really fancy and squiggly, or you can just try and just commit. I mean, once I've done it, I just commit. I don't think about it. I just draw that. So sample space is the set of all the outcomes we can have. So if we go through tossing a coin, we'd have two possibilities, heads and tails. Notice they're in the squiggly bracket, meaning it's just a group of outcomes we can have. If I were to roll a die, 6 possibilities as long as it's a six-sided 1, 2, 3, 4, 5, 6. So this is the set of outcomes we can observe. Now why this matters is you all probably think of probability as some number over another. Well, that denominator is always the number of objects in the sample space. It's all the outcomes we can have. So if I'm starting to work with probability here, say I'm tossing a coin, well, it's of the two outcomes, the one I'm observing. Well, there's only one of two here. So we'd say this is a 0.5 probability. If I'm saying the probability of heads, we'll get to the notation in a second, is one of the two outcomes, which are equally likely. So it's 0.5, or we can convert it into 50% of the time. Now, when I roll a dice, we talk about how many objects are in this. So 1, 2, 3, 4, 5, 6 objects. So of the 6, this denominator is always the number of objects in the set, which is the sample space. Let's go back one more thing. When I talk about, oh no, I know it's a head, I'm actually going to jump up one slide and find this. So when we're finding probability, we'd say the probability of an event, which is just something we're interested in recording, the probability of an event A is equal to how many objects are in that event, so the number in that outcome. So say I want heads, well, there was only one heads there out of the total possible outcomes, which is n. We say this is the number of objects in set U. So we're kind of going a little ahead as we talk about sets, but I can also say the probability of some event A is what I want to happen or what I'm interested in. And I like to define this in simpler terms over everything that can happen, or all the outcomes that can happen. So eventually finding how many different outcomes can happen gets to be a lot of work. So one way we can notate this is with what we call a tree diagram. So a tree diagram will show the sample space. So say we want to show the sample space of flipping 2 coins. Well, I could go through and I could say, well, the first one can be heads, the second one can be heads. That's one outcome. And if we're doing squiggly brackets, I can say the first one can be heads, the second one can be tails. I can say first one's tails, second one's tails, or third one is tails, second one is heads. So we can go through it like this, but there's other ways of structuring this. And we'll actually do a tree diagram and what we call an array, or a sort of grid way of doing it. So we'll look at 2 ways actually. other than just listing them. Because if I say flipping 3 coins or 4 coins or 5 coins, it starts to get to be hard to keep track of what order they're happening, because order matters here. So if I think about this as a tree diagram, and I say, well, here's my first coin, or first flip. We're flipping 2 coins, so this would be the first coin. I can say there's 2 outcomes. So I branch it in 2 ways. So we're starting, oh my, this is getting messy. We're starting with our first flip right here at this intersection, and I'm saying I can have 2 outcomes. I can have a heads, or I can observe a tails. There it is, first flip. Those are the only outcomes. Now if I flip my second coin, now I continue this branch, so I basically take this and I reset it and I create it again off of H. So if the first one's heads, the second one can still be that same outcome. It can be heads or tails. Or if the first one's tails, the second one can be the same outcome. It can be heads or tails. So this is called a tree diagram, and the way we read it is I just go along the branch that I'm interested in until I followed every single branch and every outcome. So here I would have first one's heads, second one is heads. So that is the outcome observed of HH. I can say, well, the first one's heads, the second one is tails, so we're going heads, tails, that's our second outcome. I can go along now because I've exhausted heads. There's no other way I can go here. I start on tails, and then I go to tails if we're staying consistent, TT, and finally last one would be tails, and then I navigate to heads. So tails, heads, and we've exhausted every branch. Every single branch has some sketch on it. So this is one way we can observe the sample space. So we'd say there's 4 outcomes, and those are 1, 2, 3, 4 objects in the sample space. The other way we can do it is with an array, or a grid. If I say this is my first coin, there are 2 outcomes. I can have a heads or I can have a tails, and that's all that can happen. We can have heads or tails. Now if I flip the second coin, say over here, I say here are the outcomes of the second coin. Again, I can have heads or I can have tails. So now I kind of have created this array of outcomes where I just combine the letters and I have every single object in the sample space. So I'd say, well, this box is heads and heads, this box is heads and tails, this box is heads. If I'm reading it, let's see, we're putting this letter first, this letter second. So this one would actually be heads, 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 tails, if we're consistent in the notation. This one should actually be tails, heads, and this one would be tails, tails. So there we see our sample space, but really what we're interested in is just there's 1, 2, 3, 4 objects, or probability is always over 4. We're going to skip this one. I'm not interested in that right now. Theoretical probability, like we said, is just what we'd actually expect to have happen. So if we go through a couple examples really quick, we'll just run through these, and you're going to have some practice on some totally fair dice games that I've come up with. So we have a basket with 3, 4, and 5 different colored tickets. That's a total of 9, 12 tickets. So my sample space is 12 objects. So we want to determine the probability of selecting a green ticket. And I'm going to grab a calculator real quick, because there's a lot of ways we can actually notate this if we'd like. So say we want to select a green ticket. So I could say this as probability of green. So probability of green happening is how many of them are green over how many outcomes there are possible, and that's 12. So here 3/12, we can fully reduce this to 1/4, or we can say this in the probability as a decimal. We can say this is 0.25. Any of these notations are okay. I'd prefer one of these two though in the end, one of the simplified ones. So now if we go to the next one, probability of green or yellow. So we're going to have a way of notating this come Wednesday or next week. So I'm not going to write this as probability because I don't want to get too much built into this. But we have 12 outcomes still. And in probability, one important piece of information to follow is whenever we say or, we're adding outcomes together. So if I want or, I say green or yellow. Well, there's 3 green, 4 yellow, so 7/12. So this does not reduce, so we could write it as 7/12, or we can do 0.583 is the probability. Now, if we wanted an orange ticket, well, of the 12 outcomes we have, how many of them are orange? 0, so this is 0 as the probability. It can't happen. That would be never happens. Finally, we'd have a green, yellow, or blue ticket. So of the 12, green 3, or tells us add, yellow 7, or tells us to add 5, 12. So the probability of selecting a green, yellow, or blue ticket is 12/12 or 1. So an idea is just, we always want to look at the sample space. That's the important part here in these, is to always pay attention to how many outcomes are there in the sample space. So that's going to wrap it up for this lesson. Go ahead and move forward onto the next assignment. This one is one that's going to take some time. My advice for you, since you made it to the end of the video, is to look up the sample space of rolling 2 die, because the order matters. If I roll a 1 on the first die and a 2 on the second die, that's unique. It's different than rolling a 2 on the first die, 1 on the second die. So look up an array or create an own array, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 of rolling those 2 die. I hope this video helps. I talked a little longer than I was hoping, but I think that it's meaningful and positive in where we're headed. So let me know what questions you have. Send me a private message, send me an email. Please communicate with questions you have. We'll see you in the next video.